Hello everyone, my name is Raghunath. I am an independent mobile application consultant. Architecture and legacy code bases are two of my favorite topics when it comes to engineering. And these days I spend most of my time dealing with legacy code bases. In this talk, I'm going to talk about three simple ideas that can have a profound impact on the kind of applications that you build. I've tried these ideas with command line applications, mobile applications, desktop, as well as server-side applications, and then they scale really well and then have similar impact on all these areas. And I hope you can also take these ideas and apply to your code bases and also reap the benefits these provide. And a little bit of a heads up, like these are ideas that I did not invent. These are not my ideas. These are ideas from other languages and programming paradigms. I am just like presenting it to you here so that you can also go and build applications that are like really robust. When we talk about robust applications, most of the time we spend reading code, right? So if you are a developer, you probably would be spending 50% of your time writing code, and the other 50% of your time would probably be spent on reading code that either you have written or someone else has written. So it becomes supremely important for us to communicate these ideas across team members. Let's go ahead and take a very simple example. So this example is going to illustrate on how we're going to make API calls to Expo system. So here we have a protocol, and then the protocol has a single function, so called sign up, and it is taking two parameters. One is an email, and the other one is a password, and then it's going to return a response. So that's it. It's a very simple API call. And in real world, this would be an asynchronous call. But then to keep things simple, I've modeled this as a synchronous call. So let's go and take a look at what response does. So when you look at the return type, it's an nullable type. So what are all the things that it can do? So first, it can successfully create a user account, and this is a very happy, it's a happy path scenario, and it can sign up a user. Otherwise, it could return nil. So when it returns nil, I have no idea what it is doing here, right? I don't really know what's going on. You probably don't have any idea about what's going on either. Because nil is a universal sentinel value, and then it has different meanings based on context. And unless there is additional information available along with the nil return value, we don't really know what is going on, right? So there's a little bit of ambiguity here. And then we can also get other errors like from the network, right? And then there are different kinds of network errors that we can have. Some of them are under your control, which means you can change the request and then you would get a valid response. And there could be something else like that are not totally under your control, right? Like say, for example, if there is a server error or you are not connected to the internet. So these are things that you really can't do much about. So if you were a person who's going to call this function, like let's take a look at how your emotions could look like, right? So if the API call goes through, you're going to be quite happy with it because you achieved what you want to achieve. And sometimes when you don't really know what's going on, say for example, when the API call is when the endpoint, when the function is going to return a nil, you don't really know what is going on because you are not the person who wrote this protocol. And then when it blows up, like when the method throws an exception, we're like oftentimes we are taken aback because we don't really know what is going on, and it's a situation that has to be dealt with anyway. So here's where I want to introduce the robustness principle, also known as the postal flaw. So the robustness principle says, be conservative in what you send and be liberal in what you accept. And these are the keywords. So associating conservativeness with sending and then being liberal when you're accepting things, right? Let's go back and apply this to the protocol that we already looked at. So if you look at this protocol, so the things that we are accepting are the method parameters, and then The thing that we're sending out is the return value, right? And let's take that robustness principle and then try to apply it over here. And if you look at the return type, currently it's a response that can be nullable. So the first thing that I'm going to do here is I'm going to get rid of null, right? And then we just have response. It's not that big of a change, but then we're getting there. So first, let's define the specification for the response itself, right? Like we need to understand what response can do. So the response can represent a successful creation of a user account, or it could also mean it could also represent that an email email address already is registered, right? And then it could also represent validation errors. Maybe the format of the email is invalid, right? Or like a particular TLD is invalid, or a certain domain is not allowed to register with the service. And it can also represent connection errors due to connectivity loss or like bad connection. And it could also represent errors that happen because the server or the gateway was unavailable. And there's also another category of errors where we don't really account for when we are building applications. Say, for example, this could be something related to deserialization of JSON responses. And this is something that your deserialization library may not be able to handle. Right? So whether we like it or not, we have to deal with all of these conditions either proactively or reactively. But then like over time, most of these gets handled if your application lives long enough. So how are we going to deal with this, right? When we have like these 6 different ideas that we have to deal with, what is the best way to go about it, right? And enumerations are one way to do it. And it's a commonly available language construct for many different languages. And you would have, and most of you would have been familiar with this, so I don't really have to explain this. So it's basically a common type for a group of related values, and you can use it in a safe way within your application. What Swift brings to enums is the idea of associated value. So you can have enums that also have values, and those values can be dynamic, right? So now let's see how we can use enumerations in Swift to deal with this situation. So now we have a enum type response. And then if you look at it, we have corresponding values that represent each of these conditions that we looked earlier, right? We have a success scenario which says the account was created. We have one of the error cases where we say that the email is already registered. And then we have another case to represent input validation failures, followed by connection errors and server errors. And then we also have a catch-all error, right? So this is how we're going to represent the response object. So let's see how we are going to deal with this. Let's say now you have this protocol, an implementation of this protocol, and then we call sign up on that and we get a response. The good thing about enum is they provide us exhaustiveness. So if you're going to put a switch on a enum value, then you have to deal with all the cases, all the values that are associated with the enum itself. So here, if the account was successfully created, then we just go ahead and save the user ID from the response object. If the email is already registered, then we're going to probably show the error to the user saying that they have the email is already registered, and probably they have to try a forgot password option. Or if there are a bunch of errors, we give them a bunch of errors and say, you know what, like these are all the errors that happened when I tried to use this email. Now you have to deal with it. And then we also have different messages for connection errors. And then we just group the server error and unknown messages together, and we're asking the user to try again after a while. So this is one way to deal with it, right? And now what happens if you are a person who's going to call this function, you're going to be quite happy because you know, like there is no ambiguity in the response object. You know what you're getting. And then you also feel a little bit calmer because like the API is not throwing exceptions, and you know all the situations have been handled really well. So what have we achieved from this? We've achieved certainty. We are more certain about the responses that we get when we are interacting with an external system. We are also conveying all the business ideas in code, right? Like in the previous case, when someone came across something like nil, they would have no idea about what is going on, right? Unless we give them additional context. But then here, nil had a meaning, but then we have solidified it by using an appropriate enum value to represent. And it also significantly improved the readability of the code itself. So it's easier to maintain. And the other thing that we're doing is we are representing all the error cases as data. So when errors are represented as exceptions, readability becomes hard because in your try catch block, the transfer of control happens abruptly, right? So when you're dealing with errors as data, it's easier to one test things out, and second, you can use the same control flow without disrupting the stack to deal with these error conditions. So what have we learned? We have learned something called as total functions, and like I didn't introduce this topic earlier, but then that's what we've learned right now. So let's go ahead and see what a total function means, right? Total functions are functions that give you a valid return value for every combination of valid arguments, right? That sounds like a mouthful. So I'm going to take a detour. To understand total functions, we have to understand its opposite. So let's take a look at partial functions, right? So now this is something that most of us are familiar with. So a partial function is a function that's not defined for all possible input values. So that's not very helpful. But then in some cases, it returns a value, okay, and it may never return at all, or throw an exception, or simply crashes, right? So that's what a partial function is. So if you look at the first scenario, we had a function that returned null, and it could have also thrown an exception or returned a valid value. So that's a partial function. But then when we use the enumerated type, we have a function that does not throw an exception, and we have a function that also returns a value for every possible input, right? So we converted a partial function into a total function, and that's why we gained a sense of security and calmness once we made the transformation. So here is a side-by-side comparison. This is the first function signature that we had. It's not very different, but then this function could throw errors if something abnormal happened, and it also returned nil. But if you look at the total function, the first thing is it does not return nil anymore. However, this function will never throw an exception, but it will also return a valid value for every single scenario that it encounters, be it a happy case or a abnormal situation. So we've learned total functions, and the other thing that we've learned is algebraic data types. Both are ideas from the functional programming world. So when we looked at algebraic data types, it's a type formed combining other types. So different languages implemented it in different ways. If you're familiar with Kotlin, Kotlin does this slightly differently. They use something called as field classes to do it, and other languages have types like union types to achieve a similar effect, right? And in Swift, we use enums with associated types to implement the same ideas. So here we have enum, and then we have the enum response itself is composed of a very well-defined set of different values. And then we have also learned robustness principle. So 3 ideas: total functions, algebraic data types, and robustness principle from this example. So where do you go and apply these ideas, right? So one of the things that I recommend is to use this in integration points with external systems, because this is the point where 2 different teams interface. In terms of a mobile application, it's basically a backend team and a frontend team. And this is at the integration point is where most of the ideas are ambiguous, right? Because your backend team is trying to communicate a certain set of ideas to you, and then you are taking those ideas and then communicating it to the rest of your business domain. So here is a place where you have to solidify what a certain thing means across different systems. And then especially, and again, like this is also recommended when you're writing anti-corruption layers. So if you have an ACL layer with, with, uh, with an Excel system, or if you have an ACL inside your own code base, maybe because you're trying to uh, reshape a part of your old system and then like uh, give it new meaning through an ACL. So you can still go apply these ideas uh, either inside or even when interacting with Excel systems. And also, I would recommend you to take into account the amount of failures that could happen when dealing with the system, because if you look at databases and file systems, they also have failures, but then they don't happen as often as it happens with the network layer. So the additional overhead that you have to put in to introduce an additional type when dealing with databases and file system is going to be a lot more, and it would not pay off compared to modeling systems uh, that fail often, like your network. So that's the first example. Now we're going to take a look into another example. This is a very simple example, and we can go ahead and apply some of the ideas. So let's say we have a function called divide, and takes two parameters. It takes a dividend and a divisor, and then it returns an integer, right? It's a very simple example. And then what we are doing in the method body is just like dividing the dividend using the divisor. So now all is well until your divisor is 0, because when you do this, it blows up. There's an exception, right? So what we're going to do now is we're going to take the robustness principle that we learned in the previous chapter, previous example, and then we're going to apply it here as well, right? So it says be conservative in what you send and be liberal in what you accept. So once we take this idea, is when we talk about things that we accept, we talk about function parameters, and then when we talk about things that we send out, we talk about the return value, right? So we are being liberal in what we accept. So if you look at this function divide, the values that you're accepting do not have any constraints. It's just integers, and you can send in whatever integer that you want. So we're being liberal in the kind of values that we are accepting here, right? And then we have a return type called quotient. So what we're doing here is we are being conservative in what we're sending out. So we try not to blow up because a total function should not throw exceptions. So we're trying to convert it into a value. And if you look at the method body, we say, hey, if the divisor is 0, then return infinity, otherwise return a result, right? So let's take a look at the return type quotient itself. And if you look at quotient, it's a enum. So we have enum quotient, and then it has two values. One is infinity, and then result with an associated integer value, right? And if you've paid close attention to the talk, now you would be wondering, like, okay, like this doesn't really change a lot, right? So we applied the robustness principle, but like not a lot of things have changed. So there are a couple of implications, right? So the first thing is uh, in the first situation, and even now, the burden is on the consumer to handle the value returned by the function itself, right? Like say, for example, in the first scenario, if there was an exception, the caller should handle the exception. But then now, even though we return a valid value, the caller should deal with both the infinity and the result types, right? Which is sort of like not very convenient. And if the consumer decides to pass down the quotient type downstream, then every single function that deals with this type has to also deal with both the types, right? Both infinity and result. So we have just increased the complexity here. It doesn't really help us, right? So if you take a look at this principle again, we can slightly modify this, right? And then take it in a different direction. So instead of being conservative in being liberal in what we accept, we try to be conservative in what we accept also, right? And let's say once we tweak this principle, let's take a look at the design implications it has. So now we have the same function called divide, and we have two parameters. The first parameter is dividend, which is an integer. Nothing changed here. But then if you look at the divisor, we have introduced a new type that says non-zero, right? And then if you look at the return type, we are still returning an integer, right? So then what we do is we look at the method body and then we say dividend by divisor.value, right? That's it. So now let's go ahead and inspect the natural number class. So with this class called natural number, and first we have something called a zero, which is a natural number, and then we have another type called non-zero that represents numbers that are not zero, other than zero, right? So a couple of things. One is we have a property that says value, and then we also have a constructor that is file private. So it's essential for us to make this constructor file private because we don't really want other people to invoke this constructor with a zero value, right? That would defeat the purpose of us having a explicit type for to represent non-zero value. So then there's more to this class. This class also has a factory function called from. So we have a static function that takes a value and then returns a natural number. And here is where the check is. It looks at the value. If the value is zero, it returns zero. Otherwise, it returns a non-zero value. So what we have achieved here is it is now impossible to call divide with a zero, right? So now we have enforced that this function can only be called with a non-zero parameter. So then what we do here is we do, if the divisor is non-zero, then go ahead and call this function. And you get a quotient. You don't really have to be afraid to call this function because you know this function will always give you a valid value regardless of what day or time of the year it is. Right? And once you, whatever you want to do, you can go ahead and do like fancy things, right? But so if you get a number that is not zero, then we fail fast immediately. So I say we are failing fast immediately here because when we construct types at the entry of a system, let's say, for example, in a mobile application, the entry to the system from the user is usually through the UI, right? And if someone is going to enter some input, and if you're going to deal with that input, but if you construct the type first, you can respond back immediately to the user telling them what is wrong, right? So that your data doesn't travel deep into your business logic and the validation doesn't happen somewhere else, right? So that's why when you build systems that fail fast, like you travel the distance through which your data travels from the point of inception to the point where it gets processed. Let's do a side-by-side comparison. We have a divide function here. The divisor is also an integer, and then we try to return a quotient, but that's not really a great idea. But then we made some tweak, and then if you look at the second example, we have a non-zero number, and then we also have an integer, which is a lot more easier to deal with, and it's a lot more easier to pass downstream. So what have we learned in this example? We've learned a tweaked version of the robustness principle, right? And where to apply? It's a very good idea to apply it everywhere inside your system boundary. So if you have domain objects, like try to model them in this way so that they carry a lot of context, and they also make it almost impossible to get deeper into the system without a valid object. So these simple ideas have an impact on the overall system design. So the first thing is you will see that there's like a lot of certainty at the code, right? Like even if you talk about smaller functions at a micro level, they are more predictable. They reveal intent and they communicate like business ideas really well. And if you build an entire module based on these ideas, then the entire component has the same characteristics as the bricks that were used to build it. And errors are always treated as first-class citizens. We no longer shy away from errors. They're treated with the same respect that normal or happy case scenarios have. And your data does not travel deep into the system. It is filtered right at the edges or at the point of entry, so that you have less errors, and the components inside or like deeper into your system have to deal with a very limited set of conditions. Also, if you are a fan of functional core and imperative shell style of architecture pattern, starting here sort of helps you move in the direction, because functional core itself is it's not a very easy thing to do, because you then have to deal with purity and immutability. I think like it takes a little bit of time for people to get used to these ideas. But then the ones that we have discussed here are also from the functional programming world, but then they are like a lot more easy, like a lot easier, and have a very low bar to entry compared to other functional ideas. And when you model your system this way, instead of thinking of objects in like managers and interactors and whatnot, you would sort of like uh, think system in terms of data flow. So the former forces people to think about who does what inside the system, whereas this style of programming enables you to think what data originates from where and how it flows through the system. So and as a nice side effect, tests also become a lot more easier to write and maintain. Again, like adding to the previous point, when you look at boundaries, most of the time when we cross a boundary from one component to another, they are over function calls. But then when you think in terms of data, those calls are represented in terms of boundaries instead. And there's also a cure against primitive obsession. So primitive obsession is a pattern where anti-pattern where we use primitive types to represent like objects that have meaning. Say, for example, we may use a double to represent currency, right? But then a currency is like a lot more complicated than that. And we may also use string to represent email, which means email itself uh, it's a complicated thing. Like even if you think of validating an email address, now you have string, and then you have this validation logic that applies on a email at a radically different place, right? But when you think in terms of types, you're putting them together, so you have an email type, and everything that is related to email gets self-contained into a single object, right? Like that's the very basic principle of object-oriented programming as well. Also reduces defensive programming. So defensive programming is when you don't really trust the data that you're receiving, and then you try to do checks every single place at every single place. But then when you make it impossible for someone to pass you invalid data, then you no longer have to be defensive when you are receiving parameters from an external system or an external caller. And also promotes property testing over behavior testing. And property testing are like easy to write and very low maintenance compared to behavior testing. So that's it. So today we've looked into three ideas. I've listed four, but then they're basically three ideas. We have the robustness principle, and then a slightly tweaked version of the robustness principle. And then we also looked into total functions, and finally into algebraic data types. That's it. And you can reach out to me on Slack or Twitter and ask me any questions that you have. I'll be happy to hear from you guys. Thank you very much.